Welcome to a video on common gate amplifier design. In this video we will look at the purpose of each component in a common gate amplifier, some design parameters and specifications, and then some design examples and simulations. So, first off, here we have a typical common gate configured amplifier. So our input impedance we will be looking in there, and input impedance is typically 1 over the transconductance of the amplifier. So the drain current controls this. So RS is important to stabilize our drain current. RG1, RG2 provides our VDS, VGS, sorry, for our bias. And it doesn't matter what the values of these two resistors is. So typically you just have a specific amount of current that you want to flow through there, and you do your component selection purely on that. You can choose them as large as you want, since they only provide a voltage. RD is going to be responsible for the gain in our amplifier. The capacitor here at the back removes these two resistors from any model that we have, not that it has a very large purpose since it is not seen from the input side in any case. Right, so let's have a look at some specifications. So you can design for a specific loaded gain. When a load is given and we want R load prime, which is just the parallel combination then from the load and the drain resistor. So AV, not AV0. Then you always try and design for ID RD equal to VDS. So the voltage across these two to be the same. Then maximum power transfer into one of these amplifiers is very typical. Since it has a very low input impedance, this is ideal for antennas and transmission lines and whatnot, and selecting a low input impedance and then working with power transfer. Can also design for maximum power transfer out of an amplifier or maximum voltage transfer out of an amplifier where the load is about 10 times larger than the output impedance. So those are the typical things to design for. So we only have two configurations that we can use for the common gate amplifier. So this is the dual rail where the input comes in here. So RS is then just responsible for the bias. RG is to provide a nice DC path for Kirchhoff's law here. And the drain resistor is responsible for the gain. And we have a voltage across those two to be the same, and that's VDD over 2. Okay, then the single rail application, we have two options again. We have these two voltages the same, add the extra resistor, so we can use VDD over 3, or we have a smaller VS value, and then we keep these two the same and just use a different VS. So VDD minus VS over 2. So those are the three typical things that you can do. The common gate in summary. When looking into this, we see RSS and GM in parallel, with RSS being a large biasing resistor. It will typically be much greater than 1 over GM. So the input impedance is 1 over GM right there. So that is usually the starting point of your design. The output impedance is the same as a common source amplifier, so Z out is RD parallel to R out. Assuming R out is infinite, our output impedance is just RD. We have the same gain as the common source amplifier, it is just not inverted. So the common gate is a very simple amplifier to design. Again, loading effects. We will be working with mostly with matched loads on the input side. So this will typically be a half if it's matched on the output. You will also have a half here if it's maximum voltage transfer. It would be 10 over 11 if you go with 10 times smaller selection. Okay, so those are the typical things around a common gate amplifier. So first example is we need to design using a VDD of 12 volt, a transconductance of 1 amp per volt squared, and a threshold voltage of 0.5. Specifications, input impedance of 50 ohms, and a current of 100 microamperes flowing through these two resistors. You can make this 1 microampere if you want, doesn't really matter. We'll just scale these resistors upwards. For the common base, this is purely a voltage divider that you are designing here. Okay. Assumption signal resistor of 50 ohms, and nothing was said about RD, so we can just go with standard maximum swing design. But R sig being 50 ohms means that we have matched input impedance and input load, so already the gain will half right here at the beginning. So let's jump into our design. So first we can write down everything we know about this amplifier. I've taken out the output resistor since we don't have any information about that, and our small signal simplified to something looking like this. Now, our starting point would be 1 over the transconductance and our input impedance. With our transconductance and choosing a drain resistor, we have our gain. 3 resistor, single rail, so VDS is ID RD, ID RS, and just a voltage divider for the 2 gate resistors. Having a current flowing through the 2 gate resistors of 100 microamperes, the total voltage there is 12 volts, so 12 divided by 100 micro will give us the combination of these 2 resistors. Right, so 1 over GM should be 50 ohms. That gives us a transconductance of 20 milliamperes per volt. We can get out the drain current required. That's 200 microamperes. VDD over 3 gives us 4 volts. That will give us 20 kilo ohms per resistor. The closest is 18 kilo ohms or 22. That will just decrease this drain current right here. So our output impedance in the end is 18 kilo ohms due to the choice of RD right here. The gain of our amplifier is 18 kilo ohms times 20 milliamperes per volt transconductance. So the maximum gain here is 360 volts per volt. So yeah, the gain of this amplifier can be quite large. With the drain current calculated, we can find our VGS value, and that is 0.5 2 volts. That is only 0.02 volts larger than our threshold voltage, so this is a very dangerous area to work in for this amplifier. We are very close to going into the triode region, or being in cut off rather. Calculating our VS, it's 3.6 volts with the chosen resistor value, and that will give us a gate voltage of 4.12 volts. That can be plugged into our voltage divider. A combination of the two resistors with 100 microamperes flowing is 120 kilo ohms. Plug 120 in here and we can find our second gate resistor first, and that is 41.2 kilo ohms. Closest is 39, and with that RG1 will be 81 kilo ohms. Closest is 82 kilo ohms. Right, so AV0 from what we've seen is 51.1 decibels. Our loaded gain is 9.9 kilo ohms, and that will give us 198 volts per volt or 45.9 dBs, and the input being matched, so 50 over 50 plus 50, so half, so will give us 99 volts per volt or 39.9 dBs. So we designed for matched input impedance, and we designed for maximum swing. Let's see what the simulation gives us. So here is our simulation. I've taken the liberty again of doing the calculations beforehand. So drain current of 186 microamperes. So it's here around 186 here in the middle. Here we have 8.66 volts, subtract 3.3, that gives us around about 5.3 volts VDS. And I'm inserting 1 millivolt peak and getting out just under 100. And our final gain was about 100 volts per volt. That's even with the input impedance being matched. So if we make this 1 milliohm at the source, this should double, okay, almost 200. And if we make this a very large resistor, let's say 10 meg, it should go to around about 360 and 350, because we had to choose standard components. So the simulation correlates quite well with our designed values. Let's do the AC analysis quickly, then we can see it in decibels with our frequency response. So this is our maximum gain at 50.8 dBs. Make this 22 kilo ohms. This is our loaded gain at 45.7, and then with a matched input, it should drop with 6 decibels, 39.7, 39.8 ish dBs. And that is our first common gate design. Okay, correlates quite well with our calculations. Let's go to the second example. Our second example is take a common gate amplifier loaded with 22 kilo ohms, 15 volts positive rail and a negative rail, 100 milliamperes per volt squared transistor, threshold voltage of 0.5. We should design for maximum power transfer with our signal of 100 ohms. So looking in, we should also see 100 ohms. design for maximum swing again, and calculate the rest of the parameters. Okay, so not much changed here. This is derail, so RS is purely responsible for our bias. RG, you can choose anything you want. And the rest is kind of standard, remains the same. VDS is IDRD is VDD over 2. Okay, so designing with that, we get a transconductance of 10 milliamperes per volt, gives us a drain current of 500 microamps, and a VDS voltage of 7.5 volts. That gives us a drain resistor of 15 kilo ohms. Plugging in the current that we had in here, we get a gate source voltage of 0.6 volts. So this is much safer than the previous design, not so dangerous. Our overdrive voltage is 0.1 volt, still not 0.2, but it is already better. It's a little bit farther away from being in cutoff. The previous problem, you couldn't insert very large input voltages. With this one, it can increase quite a lot. Right, so that is drain resistor. This will give us source resistor, so minus VSS minus VGS. So 0.6 being much smaller than 15 volts. It's actually quite easy to design for this, and you get 28.8 kilo ohms, standard value 27 kilo ohms, gate resistor, pick at 100 kilo ohms, and your design is finished. So this is quite a quick design for a common gate amplifier. Checking our results, our transconductance multiplied by our drain resistor, 150 volts per volts, and 15 volts rail divided by 0.1 give us 150 like this. So this is maximum gain like we had it in the common source problems. That's 43 decibels. Taking the loaded gain give us 89.2 volts per volts, and with a matching input impedance that will take us down to 53 decibels or 44.6 volts per volts. So quick and nasty design for a common gate amplifier. Let's have a look at the simulation. This was also the final example of this video. So here is our amplifier, 27k, 15k's, 100 ohms here on input. I took the liberty again of getting the values beforehand. So 7.6 volts is close to the 7.5 we were designing, and this is also close to the 500 microamperes we were designing for, and these values correlate quite well with the ones we calculated in the analysis part of the design. So if we run this simulation, we insert 10 millivolts peak. We measure here, it's roughly half, so 5 millivolts peak. So we have a perfect 100 ohms input here on the source. And if we multiply this with 45, it should go up to 450 millivolts peak. Right, so let's check this for our loaded gain and our maximum gain. Make this 1 milliohm. So 1 milli in, almost no loading effects. and output is a bit more than 80. So halfway, so yeah, roughly 90. So loaded gain close to 90 millivolts peak. Sorry, 900 millivolts peak, but 90 volts per volts gain. Make this 22 mega ohms. That will show us amplifier's gain, and that seems very close to 150 volts per volts. So this amplifier is responding as designed. So yeah, there's how you design a common gate amplifier. Thank you for watching.